It's great to be here. Okay, so anyway, so here's an outline of the talk. So first I'm just going to talk about a kind of a little theorem, and this will maybe bear a passing resemblance to some symplectic geometry, and then some more things will come back. Then I'll talk a little bit about the famous square peg problem, then I'm going to show you a kind of a computer demo of these things, and then then I'll talk about rectangles, maybe an up to the minute survey or something, or I'm not sure if it's up to the minute. More demos, and then I'll talk about the main results. So that's the plan. Okay, so here's the toy theorem. So you have two. So this is a picture of two curves. There's one on the top and there's one on the bottom. And you start with a square, although it could be a rectangle of constant aspect ratio, say a 2x1 rectangle or square root 3x1. And the thing is supposed to move, and the top 2 points are supposed to always stay on the top curve, and the bottom 2 points are always supposed to stay on the bottom curve. So it's like a cross-country skier. And then the theorem is, suppose it goes from the start to the end. It just goes through here continuously and it gets to the other side. Then the theorem is that the width here is the same on either side. It can't be squeezed at all, no matter what that's the result. So as long as it's a square and it starts like this and it ends like that. So that's the toy theorem. So I'm going to talk about the proof of that. And then go on. Does it make sense?
You say the vertices, not the edges.
That's right. That's a good point. As this thing moves, the edges, if it's here, the edge won't be on the curve. It's just the vertices that count. So you just want to know, can you move this thing across, and can you make it across? And then the answer is no, unless maybe you can't anyway. But the only way you can make it is if the width on either side is exactly the same. So I'm going to kind of explain the proof of this. So there's an invariant. So A of t is the area of the square, and B of t, the square kind of cuts off it makes two loops with the curve itself, and you orient it so that it would be positive if everything was inside. Okay, so B, I guess B of t is what's left over, and then the invariant is you take 1/2 A of t minus B of t, and then the claim is that this is a conserved quantity. So this quantity, I should say that there was a paper by Terry Tao on this, and this invariant is quite similar to the invariant that he found, but he used. So maybe I'll just quickly. So if you believe this, then if these have different widths, then the answer is it's different. It would be 1/2 A of t on one side. So the answer, unless it's the same size, it's a different answer. So what's the proof of that? So I'm going to talk about something more general. This is you could ask more generally, what happens if you have a rectangle that moves across, and you're allowed to vary the aspect ratio? Then what I'm calling C of t is just this invariant A minus 1/2 B at each point. And then what it turns out to be true is that you take C of t minus C of u, and you just take this path is computing the length and the width of the rectangle. And you just make this curve, and you take its signed area. And what I'm saying is that this is a more general case, and it reduces to the case if this has constant aspect ratio, then the curve just stays on the diagonal, and then it's 0. So another way to say this is that there's the, as everybody knows, the contact form x dy minus y dx. And what I'm saying is that this is really the integral of the contact form along the path that connects them. So that's what so there was a passing resemblance to contact geometry. But anyway, so this is, how do you prove this thing? I mean, this is just calculus. I mean, you just differentiate with respect to time, and maybe you don't have to follow this, but a is x times y, and dA is x dy plus y dx, and dB turns out to be y dx. It's just a calculus problem, and then you see that the differential of this thing is just it's just this one form, and then when you integrate, you get the signed area. So that's the more or less the proof of that Tory theorem. So far, so good? OK. So I wanted to give an example. This is an example of a this is a little different situation because the square doesn't start out on two parallel lines, but this is sort of two kind of a polygonal logarithmic spiral, and this is supposed to suggest that you can just take a square and kind of move it along and shrink it all the way down to a point. So somehow the fact that you start on the the invariant is 0 in this case. So this is just sort of, there's something necessary about the thing starting in a certain way. OK, so the square peg. OK, so here's the square peg conjecture. So a Jordan loop is just the image of the circle under a continuous injective map. So I do some kind of a piecewise smooth Jordan loop, but the thing that gives people trouble is things where they're like fractals, things like that. So every Jordan loop has an inscribed square, so 4 points that make the vertices of the square. So this is Toplet's conjecture from 1911. And here's some results about this. I guess quickly proved in the convex case. It's true for smooth loops and polygons. Later, I'll kind of explain a proof, more or less, that it's true in the smooth case. Then this one, Meyerson's theorem, this is not related to squares, but it says that all but at most 2 points of any Jordan loop are vertices of inscribed equilateral triangles. So that's sort of a related result. Then there's this result if you have this is supposed to be an annulus where the inner radius is 1/2 the outer one. And if you have a curve that loops around it, then it's true. And then there's this theorem of Terry-Tallis, which is you have a region which is like between the graphs of two functions, and the functions are distance decreasing. Then it's also true if you have a region which is locally the graph of a function. You can also prove it there. So somehow this is like, this made me feel a little bit better. Like this is sort of a technical result. And so, but anyway, so then there was this article. One place to read about all this is Igor Pak's online book, Discrete and Polyhedral Geometry. It has like a long history of this problem. And I mean, I don't even know the whole history of this thing, but this is some of it. I don't know. I mean, yeah. I mean, I don't know. No, I don't know what made him think about this. OK, so now I have to give you a technical definition, which is not hard, but it's just because that's what my computer program does. So I want to say what I mean by a graceful inscribed square. So if you have an inscribed square or rectangle, then there's two cyclic orders on the vertices. One comes from the cyclic order on the square and one from the curve. And so here the orders coincide, and that's what I mean by graceful. And here they don't. Like you go 1, and then if you follow the curve around, you don't go around the vertices in order. So I'm only going to be interested in these graceful ones, although a lot of what I say just works the same in general. So OK, so now I'm going to show you. Oops, that's the wrong program. Sorry. OK, so now I'm going to do a kind of a computer demo. So there's a triangle, and there's 3 squares. Now there's 1. Now there's 5, 7. So while you're looking at that, let me tell you maybe the question that really people are that I think is really neat. Like the square peg problem is true for things like smooth loops or polygonal loops, and so the natural way you would try to prove it in the general case is you would approximate your fractal curve or whatever it is by a general one, and then you always know that you have a square, and so you just say, well, I just take a limit, and then you're done. But the problem is it could shrink, and so another conjecture, which another popular conjecture is that's called the polygon fat if it has a disk of in radius 1. So at least there's some point that's 1 from the boundary. Then the conjecture is that a fat polygon has a inscribed square of say side length 1/10. So in other words, but 1/10 is not important. It's just some epsilon greater than 0. So a fat polygon is supposed to always have a big square. And so that's what's nice about that conjecture is that it just involves polygons. And if you could prove that, then it immediately implies this other thing. And it's somehow some kind of qualitative result that goes beyond just topology. So anyway, if you look at this thing, I'm always terrified when I run this program because I'm worried it's going to show there's none, but there's some bug. But anyway, okay, so what does it do? Okay, so what it does is that if you, so firstly, I only consider generic polygons, so there's no parallel sides. So every square involves either 3 or 4 lines. So let's say the case of 4 lines, you could say, well, if I have 4 lines and I put one vertex on each square, well, then there's some kind of algebraic equation. You can just find them all. So this thing just enumerates all the triples and quadruples of lines. It finds all the inscribed squares, and it just removes the ones that are not actually inscribed in the polygon, but rather just in the thing itself. But you see like lots of big squares. The other thing is this number 7 is counting the number of polygons, and you might notice something about this number. It's odd. And look closely, like you can take this thing and you can sort of very gently move it. Like there's okay, maybe I can make it even gentler. So this is like right before the end of it. And so what's going on right at the end is that sort of if none of the vertices is near a side and you move this thing around, it's stable. I mean, there's no change. It's the only thing that can go wrong is when a vertex goes into a corner. And generically, if you take a kind of a generic variation, this happens just for one of the vertices, and they cancel in pairs. One of them is sort of moving this way, and I mean, there are various cases you have to analyze. Maybe the next slide has this. Yeah, I mean, I just made a picture of this, like what can happen in a generic variation. This is supposed to be the polygon, and like one of the vertices can be moving this way or this way. There's several possibilities, and in all cases, you notice the parity doesn't change. So the idea is that you start with some polygon where you know the answer, where it's 1, say like a convex triangle, maybe triangulated a lot, subdivided a lot so that you can then move it around. Then you take a generic variation to your favorite polygon, and the parity doesn't change. And so the final answer is odd, which is non-zero. So that's a proof for polygons, roughly, that every polygonal loop has an inscribed square. And then for something like smooth, you just if you have some kind of approximation to a smooth square, the thing can't be shrinking down because you'd have to have 4 points somehow that were a smooth curve is almost flat. So there's no way it can support. That polygons near it can support small squares. So just when you take this limit, it works in the smooth case. And even if you're careful, you can take the limit even when it's locally the graph of a function. Like, if it's the graph of a function, the thing, maybe it has to kind of go up and then around like this, and it's not the graph of a function. So even in that case, you can do it. If you only use like these graceful squares, you can prove that. So that's a sketch of a proof that for smooth and polygonal loops that there's always a square. So OK, but then that's all I got for that. So here's some work about. Oops, no wait. Where is this? Hold on. Where is it? Sorry, I'm looking for my slides. OK, hold on. Well, maybe I'll just tell you. So rectangles. I don't have a slide for this. So one of the results is due to Vaughan, that every Jordan loop has a rectangle, and another result is due to Cole-Hugelmeyer here, that every smooth loop has an inscribed rectangle of aspect ratio √3. and other values. It's just that √3 is the one that works all the time. And this is, this kind of goes through knot theory, I'd say. I mean, it sort of uses, there's Vaughan's proof kind of embeds, well, it involves an embedding of the into R3. And, well, it somehow, I'm not going to explain his result, but it kind of relies on some serious technology, I'd say, from knot theory. There's also a result that every, which my result is going to be better, but there's independently of me someone proved that for any Jordan loop, a dense set of curves are vertices of rectangles. So I can't seem to find my slide on this, but that's all it says. So one conjecture about rectangles is that for any smooth loop, let alone non-smooth, any smooth loop in any aspect ratio, you can always find one. So far,
what was the theorem you mentioned, √3?
That for any smooth loop, and you can do it for √3.
Magic numbers that
Yeah.
Aspect ratios that you can do.
Essentially, if you have a regular polygon with an even number of sides, you're guaranteed that at least one of the rectangles for the corners of that has that aspect ratio inside it. So it just so happens to be that for a regular hexagon, all of the rectangles are aspect ratio √3. So you're guaranteed to have.
So you said there's the dense set. What is it? Category 2 or something?
Well, I'm gonna prove something better, so I won't talk about what they get. So now let's look at rectangles. So there's rectangles. I'm gonna turn off this number because it only counts as so I'm varying a slider which is changing the aspect ratio, and it's computing all the rectangles. Doesn't have to be odd now, but one thing. So here's a neat fact. One cool theorem that I noticed. The same thing I was saying with the 4 lines, it also works for rectangles. And there's a beautiful fact. If you have 4 generic lines, and you look at all the rectangles that are inscribed in them, so point 1 is on line 1, point 2 on line 2, et cetera, then the locus of centers is a hyperbola. So it's really a nice, you get a kind of, as you vary the aspect ratio, you get a kind of a nice one-dimensional manifold. So here you're sort of seeing, I mean, what's happening here? Like as this goes along, I'll change the shape just for fun. What are these limits? Well, geometrically, in the smooth case, it's easier to see. But if you have an inscribed rectangle that's very long and thin, then the sides on the top and the bottom are practically tangent. So the long side is practically perpendicular to the tangent. So in the limit, you get a critical point for the distance function, and this makes sense even for polygons. It just means that the perpendiculars to the chords don't locally separate the polygon, and so generically this space is a one manifold. I mean, it's a combinatorial one manifold, and the components that you're seeing as you go through this path are are the arcs. But there are also some loop components, potentially. But you can't see them in this picture. You can compute the space. So I just pushed a button, and this manifold has 9 components. And the way it works, what the computer does is it. Let me turn some of this junk off so you can see it. So these rectangles are special. The ones that are indexed by these boxes they go through vertices. So what the computer does is it computes all the special rectangles, the ones that have a vertex, and then it looks at them in pairs, and it decides whether they are actually part of a path of rectangles. So for example, there's this one, and then this one. If you look at it, like these share a side, and these share a side, and these share a side, and so they all share sides, and that's necessary for them to actually be in the same component of this manifold. It's not quite sufficient. There's some kind of discriminant you have to compute involving the various coordinates, and if that's positive, then they are actually connected. So, but anyway, the computer is happy just going through, and it's doing this. And so, let me just see if I can get this to work. Right. So this shows one of the components of this manifold, and so. There's some interesting things I'm going to point out about this. I'll just let it run. So I've colored the points. The endpoints are these chords. And I've colored them according to their Morse index. So in other words, the red ones are local maxes. And the blue ones are local mins. And the pink ones are saddles. And one thing I've noticed from thousands of examples is that it always happens that the paths jump Morse index by 1. So in other words, that when you have this really whatever kind of complicated polynomial you have, you write this thing down, and the Morse index always jumps by 1. So I don't know how to prove that, but do you guys see what I'm saying? Like that if you look at a path of rectangles that connects 2 critical points of the distance function.
Morse function?
I don't know. What's the function? The function is the distance. The distance is defined on pairs of points on the. So I just mean by the index that it's that if it's a max, the index is just the number of endpoints you can vary to lower to decrease the distance. So I mean.
And you mentioned it's not a tree. The space of inscribed rectangles has a pi 1. Like, do you know something about?
Yeah. So there's some loops. I mean, this bottom one is a loop. I would be happy if it was a tree for reasons I'll explain in a minute. So in fact. Well, I'll explain. So there's a little more, let me show you a little bit more. You can plot the shape. So in this example, this component that I'm plotting, it starts out long and thin, and it ends up thin and long. In other words, the aspect ratio changes from 0 to infinity if you keep track of the labeling of the sides. And if you compute this area that goes, so you take the region that just, the kind of obvious looking region here, then the area of this region is exactly equal, the signed area of this region, it might not be embedded, the signed area of this region is exactly equal to the area bounded by the polygon. And that's just an application of that integral formula I talked about in the beginning. So these are kind of, I call these components hyperbolic components. They sort of start like this, and they go like this. Sort of, they have this kind of motion. And these other ones, the light green ones are the hyperbolic components. And then these other components like this, maybe I'll do this. Here's another one. This one is kind of boring. It starts at aspect ratio 0 and it ends at aspect ratio 0. So this one. If you take this region here, its signed area is 0, and that's also a consequence of this integral formula. So one neat thing about that is that since it has signed area 0, it has to have a self-intersection. So there's two rectangles that are isometric to each other that are inscribed. So I'm going to talk about that later. It's not following it now. But OK. This program is not completely bug-free. OK. There we go. Now it's fine. So, OK, so the next thing I want to do is give you a false proof of the aspect ratio conjecture, which I thought was a real proof, and then I sent it to Cole, and then he said, no, here's a glitch. So here's the proof. But it's wrong, but here's the idea. It's going to still give me something that I'm going to use. These hyperbolic components, they have an odd number of squares along the way because they cross from here to here. And these other components, these kind of trivial components, have an even number of squares because they start and end on the same axis. And since there's an odd number of squares, there's always one of these interesting components, and this interesting component goes through every aspect ratio. And QED, except there's loops. But obviously, the loops kind of have an even number of squares on them. So there's one glitch, which is that you can have a component, in principle, you can have a component which it's a path which comes back to itself, but the vertices have been cycled by one click. So in other words, it's a path in the configuration space that's invariant under the cyclic relabeling. So those have an odd number of squares in the right sense. So all I can prove, all you can really get from this is that there's, I call those elliptic components. There's either a hyperbolic component or an elliptic component. But if you think about it, they're both good in the sense that both of them sweep out the entire curve. Like the hyperbolic components, if you think about like case of an ellipse, they omit at most 4 points, and the elliptic ones get everything. So at least in the case of polygons, all but at most 4 points are vertices of these inscribed rectangles. And the next thing I want to say is that what's nicer about this is that it's easier to take a limit of these paths of rectangles, because if you have a path of rectangles that goes throughout the whole thing, it's frequently large. Like it can't sweep out the whole thing and stay small. So there's frequently places where it's going to be big. And so the way I'm just going to say this intuitively first, and then I'll say what the theorem is. But you imagine you've got some Jordan curve that you can't understand, and you've got some nearby polygon, and you look at one of these paths, these global components, either hyperbolic and elliptic, and the square size, it's sort of, maybe it goes like crazy, but you can look where it's big, and then you can sort of go down until it gets small at either end. And you can take a limit of things like this, and you can still get a kind of a connected component of squares, of rectangles that kind of fills out the whole Jordan curve. So maybe a nice analogy of this is like if you look at like a surface that's evolving under something like a mean curvature flow, it's like pinching off all over the place, but you can still look at like one of the nodes. It still has like this one big bubble or something. So anyway, I can say what my theorem is, and I'll say a little bit more about the proof, but that was kind of the idea. Okay, so let's see. So here's my theorem. First theorem. So for any Jordan curve, there's a connected subset of gracefully inscribed rectangles satisfying one of the following. So firstly, one possibility is that you get every aspect ratio, and at most 4 points are admitted. So this is great. This is the square peg conjecture and more. This one says that every point is the vertex of a rectangle, and the area is the boundary. So this is the case where the thing kind of just rotates around. And then the final theorem is the unfortunate one, which, if this wasn't here, it would prove the conjecture. But anyway, you can have a connect. So at most 2 points of the curve are not vertices of rectangles, but then there's rectangles of arbitrarily small diameter. So this is why I didn't bother to explain, like, is this dense set of second category or not. This says that all but for any Jordan curve, all but at most 4 points are vertices of inscribed rectangles. So that's what you get. And like I actually think in the smooth case that this rotating component, this elliptic component, that it can't actually occur. I've never seen it. I've never seen one of these rotating components in all the experiments I did. So I think, I don't know how to rule those out, but if you could, it would prove the aspect ratio problem. Okay, so next thing I'm going to do is I'm going to just give a sketch of this proof. What I sort of did already, but I'll say how it works. Just a little more detail. So so this is the only proof in the talk. Or if you have an inscribed, so what you do is you think of your, you have a Jordan loop and it's parameterized in some way, and so you just think of it as having a measure on it that comes from the parameter, and you also parameterize all the approximations, so they all have measures, and so it makes sense to talk about the quote length of an arc on it, even though it might not be rectifiable. It's just a measure. So if you have an inscribed rectangle, you're taking red length. It's the sum of these two over the sum of these two, and so this is a function for each loop. It's a function from inscribed rectangles into the reals, and if you keep this invariant away from 0 or infinity, the set of rectangles you get are compact, because if they get really small, just one of these arcs becomes the whole thing, and so the invariant either goes to 0 or infinity. So if you keep the invariant, say, between 1/4 and 4, then just the things that map into here it's a compact set or pre-compact set. So what I do is now let's go back to the situation I have. There are several cases. Like imagine I have one of these hyperbolic components. It goes whoosh and whoosh. Then at every stage, I can find a path that connects. Like for any n, I can find a path where one side has invariant 1/n, and the other side has invariant n, and I can arrange these paths so that they're sort of minimal. Like I want to kind of take a limit of these, and I just set it up so that I since everything's compact, I can make these nest in the right way, and I can take a limit of these paths, and the limit of connect is connected, and the compactness lets me really take a limit. So what I get is a connected set of inscribed rectangles which has every one of these invariants possible. And how could that happen? It can't omit 5 points because it just couldn't go to 0 one way or the other. So that's why you get everything. So that was one case, the case when it's hyperbolic. What if it's elliptic? Well, suppose nothing ever gets small. The thing just stays big the whole time. Then I just take a limit and I'm done. But it could be, I could get this elliptic component where like it's getting small one way or the other. But then because it connects everything to its cyclic relabeling, it connects something of small invariant to something of large invariant. So in the elliptic case, I can also do, if in the case it is degenerating, I have the same kind of limit I can take. And so it just mimics the hyperbolic case. It kind of goes way off to the side like so. And I again can take a limit like this and get a connected set of rectangles that omits at most 4 points. So those are all the cases that can happen. So that's what I mean. You get something like, it would have been nice if there was always one of these hyperbolic components, but there's both. So, but it doesn't matter. You can still take a limit of this thing and get this result. So that's the first of the two theorems. Okay. So now I'll explain the second one. And this is sort of like using the invariant to get some information which is like slightly more than topological. So what I want to count is multiplicities of inscribed rectangles. So this is going to be like, informally, it's the number of inscribed rectangles minus the number of isometry types of inscribed rectangles. So in other words, if there's a lot of inscribed rectangles that are isometric to each other, this count is large. So the way I say it is like, you give you're going to grade this thing, and if there's a k+1 tuple of congruent inscribed rectangles, then you get a score of k. So A would give you 4. And so this 8 is informally, it's the number of inscribed rectangles minus the number of isometry types. So if this is large, there's a lot of coincidences. And then, so here, OK, this is a technical thing. So a stable diameter, I just needed this for the proof. It's a diameter that when you perturb the polygon, it remains a polygon. So if you pick a generic polygon, all the diameters are stable. Then the theorem is that if you have n stable diameters, then the total score is at least n over 2 minus 1. So in other words, if you have a very complicated polygon, then you have a huge number of kind of coincidences of inscribed rectangles, pairs or triples of rectangles that are isometric to each other. Does that make sense? So I'm going to, one thing about this is that so far I've been talking about these graceful rectangles, but the argument, the same kind of stuff works for any inscribed rectangle. So this just works for any of them. So anyway, now I'm going to explain the argument of this. OK, maybe I should open up the program again. Nope, that's the wrong program. Nope, it's here. It's fun to compute a big one. OK, so you just forget the loops. Notice that all the loops have an even number of these squares, so you never see these rotating components. But anyway, for all of these components, which are kind of trivial, there's a self-intersection. There's a point. There's a point. You get one count for each of those. And then if there were 2 of them that intersected in the same point, your count would be even higher. So in the worst case, you get 1 point for each of these. And then for the ones on the top, if you have 1 of them, you don't get anything, because then that accounts for the -1 in the formula. But if you have 2 of them, then they bound regions of the same signed area. So if they're embedded, they have to intersect. And if they're not embedded, then they have a self-intersection. So again, no matter, if you look at all cases, you get a point for each of these. And so just the number of them total is just the number of diagonals. I mean, this is just computing these graceful ones. But if you also get these components for the other kind. So this is the proof of that result. Just there's this area formula gives you that result. OK. So what else can I say about this? Yeah, I feel like I went through this quickly, but maybe I can show you a little more. This program does other stuff. Like this window sort of shows where's the polygon? So this window is parametrizing the you just kind of put arc length on the boundary of the polygon, and then this bottom window is showing you arc length. and this is showing you time. So this is just showing you where the vertices actually go. So this is sort of a picture of how these things look. So I kind of was trying to, I mean, you lose if sort of, if kind of all, if on a horizontal level, all four of these points are kind of close to each other, it's a small rectangle. Anyway, so this is another way to, I was trying to study this thing, but didn't really make much progress. Okay, so let's see. So maybe I'll try to show you how why I think this approach is not going to solve the conjecture. So I'll kill that. Let's see.
So I haven't followed on. So you're finding these things on different components or always on the same component in your theorem? Or like you still have this graceful, you always...
Oh yeah, so you mean, so in the first...
when you start searching, you go to a specific component and then compare. I didn't quite follow.
Oh, so for the computer program just finds all the graceful components. This is the space of all these gracefully inscribed squares. And in the theorem, the set of rectangles that omit at most 4 points, that's a connected set.
Right.
I don't know if it's a path component. It's just the limit of connected sets. So I mean, it could be pretty wild. I wanted to see if I can show you a picture. This is a weird kind of thing you can do. So this is, I have to perturb. Hold on. Okay. There. So, yeah, so, okay, this is maybe too tough to, this is pushing the limits of this thing. Yeah, it's not. It's kind of stopping in the middle. It's too. Let me try to. This one is close to. This thing's not perfect. I mean, it has all kinds of tolerances, and it just.
What are you trying to do? Find your rectangles in that shape, and you're struggling.
I wanted to show you one where. Okay, let's look at this picture and pretend it's really doing the right thing. Like it.
Which one?
Well, look at this picture.
17. What are we doing?
What are we doing? Okay, hang on. Let me just start this thing over. Just start over. So I wanted to show you the case which. Okay, so previously I showed you this thing that was like a logarithmic spiral that kind of went around, and you can make that into a Jordan loop just by cutting it off, and then I wanted to show you what the space looks like for that. But it's kind of on the that's the number of inscribed squares. So okay, so hang on. And it's blanking out. Yeah, it's pushing the limits of what it can do. When it's red, it means it's not generic. Okay, this isn't. Okay, it's not performing. All right, it's just stalling out. I'm going to try one more time, and then I'm just going to move on. Okay, let's see if I can get something. So I'm trying to compute the space. Anyway, what I wanted to say, even if it doesn't show up, is that you find the path of rectangles, you find it, the aspect ratio stays less than 1 for most of the time, and it only dips above 1 right at the bottom. And so that makes me think that, well, I naively thought that, like that you might wonder, where are the big rectangles? That's the conjecture you want to prove. And I always thought, well, they should be on these kind of hyperbolic components. But if you do an example like this, it sort of shows that it doesn't have to be the case. You can have these hyperbolic components where the aspect ratio is less than 1 almost to the end, and then it only becomes bigger than 1 for a very small square. So in other words, you can find these hyperbolic components that only have small squares. So that's what I was trying to show in this program. But the program's just not working.
So does this mean that you disbelieve that if you have a fat polygon?
No, I totally believe it. I just think that for a while I thought that it had to be on, that this is a nice way to find them. So firstly, just look at the graceful ones. That, I think like when you're trying to prove the existence of something, it's better if there's just a few things that exist. Like if there's too many of them, you don't know what to look for. So I thought, well, let's just forget about all the rectangles or squares except for the graceful ones. And now let's forget about all the squares except the ones that are on these hyperbolic components. This would be a way to kind of limit the number of things you were looking for. But I mean, these kind of weird examples with these spirals indicate that that's not true. Like you won't find a big square in that, but there'll be a big square it sort of looks like this. And then there's just a big square that's over here, and it's not on the path that goes all the way down. That's all I was trying to say. That there's, at first I thought that, so that's what I was trying to say. But no, I believe it. I mean, I think Tverberg did numerical experiments years ago. I mean, Tverberg?
What do you believe in now?
This fat square conjecture, that you have a fat polygon, then there's a big square. Yeah, I mean, you run this program and you always see it.
So you can't build in any kind of complex analysis, conformal mapping into this, to somehow control, like with the, you think that some control, not to produce this, but to produce something that's not shrinking. I mean, the Mobius group won't help you too much.
Yeah.
You have no conformal invariant that you.
No, I don't think so. I mean, there's another result that I had on this missing slide. That if you have any convex curve, so here's something like this. This is a Kopian and Avakuma from last year. If you have any convex curve, it contains every circular quadrilateral. So a circular quadrilateral is a quadrilateral that's inscribed in a circle. So in other words, if a quadrilateral is inscribed in a circle, it's also inscribed in any convex loop. And so this is a kind of Mobius invariant thing. And so you might think like maybe.
Don't you need it to be smooth for their theorem?
I don't think so.
Because
Convex is pretty close.
Example of a convex curve that didn't have.
Really? I thought it could be any convex curve.
No, they had an example of a triangle and a cyclic quadrilateral, which wasn't described in the triangle. Yeah.
That's weird.
So,
Okay.
Yeah, so it needs to be smooth to get every cyclic quadrilateral. Smooth
Okay.
complex.
Okay.
They might have some weaker condition like C1, but it definitely.
Okay. Yeah, I mean, convex is almost differentiable somehow. Yeah. Okay. All right. But there you go. I mean, so that's pretty good. So you might ask about things like that, like cyclic quadrilaterals on non-convex curves, and that's Mobius invariant, and maybe that's better. But I mean, the other idea I had. I mean, okay, that's pretty much the end of the talk. I mean, but the other idea I had, which I've been thinking about, is that you can look at the space of let's see. Well, you can look at the space of triples of points on a curve and ordered, and then this topologically the space is a solid torus, and you can color the torus two colors. Red if the points go around clockwise, and blue if they go around counterclockwise. And then there's the interface, which corresponds to the triples of points that are on the same line. So this gives you some kind of surface that's sitting inside the torus. It's the boundary between the red and the blue. And in the case of polygons, if you put some conditions on the polygon and throw out a little bit of stuff, it really is a surface. And I have another program that computes it. But the idea is that if you had a path of rectangles, somehow you could take 3 of the points and it would have to avoid this surface. And somehow the surface, so the surface is a kind of barrier to this rectangle shrinking down. And so I had some idea that you could kind of control these paths of rectangles because they have to thread their way and stay on one side of this surface. And they're sort of protected from the boundary in some way. But all I got out of that was just like a fancy program that computes it, but without anything else. So that's pretty much. So that's what I want to try next, is think about this. The last thing I'll say, I guess a little more time, is that going back to this theorem in the beginning, imagine you have a rectangle, and it just like, and 2 of the points are on one curve and 2 are on the other. And if the aspect ratio stays constant, it can't shrink to a point. If the aspect ratio, well, it can, but the curve has to kind of go around like this. The tangent vector, the winding number around the final point has to be unbounded. So I think what's true is that if the winding number around the point is bounded, even if the aspect ratio varies, you can't shrink this down to a point. You can't take a rectangle and shrink it down to a point, keeping 2 points on the top curve, 2 points on the bottom point, provided that the winding number around the final point is bounded. And if you believe that, it would prove the square peg problem for the region between any 2 graphs of functions, not just 1 minus epsilon Lipschitz, because my option 3 couldn't happen. You couldn't shrink down to this point. So I'm thinking this would be a good avenue to try to prove, because it would at least get a really good result on this. And it's probably true that it needs to spiral around infinitely often for it to shrink down to a point. So I think that's kind of a neat question. You just have 2 arcs. They go to a point. You have a rectangle that slides along. The claim is that if the tangent vector, if the winding number around the point is bounded, then it can't shrink to a point. It's got to stop. So I'd love to prove that. But that seems like a nice concrete question that I don't know how to do. OK, so that's it.